A mass grave in the European countryside. Dozens of bodies, buried hastily. Limbs twisted, jaws frozen mid-scream. No signs of violence, only silence and bones. For centuries, no one knew what killed them. Then, a single tooth was pulled from the dirt, and inside it, a secret slept for over 5,000 years. It was the fingerprint of a killer. A microscopic assassin that spread like wildfire, long before cities, before writing, before empires. This wasn't just a plague. It was the world's first pandemic. And it left no warning, no mercy, just devastation. But why was it so deadly? How could a disease evolve with such brutal efficiency in a world without crowded streets or global travel? The answer, as it turns out, was hiding in fragments of ancient DNA, scattered beneath centuries of Earth. Today, science is digging deeper than ever before, into mass graves, into bones, into genomes, reconstructing a forgotten cataclysm that reshaped human history. What researchers found is rewriting everything we thought we knew about the birth of pandemics. How did this ancient outbreak become the blueprint for modern plagues? Long before the rise of Rome, before the pyramids pierced the sky, humanity faced an invisible enemy. It was around 3000 BCE, during the Neolithic era, when scattered farming communities were just beginning to emerge across Europe and Asia. People lived in small villages, shared tools, and buried their dead close to home. It was a time of slow progress and sudden peril. In recent decades, archaeologists uncovered dozens of mass graves from this period. From Sweden to Russia, from Germany to the Caucasus, bodies were buried in tight clusters, often with signs of panic and haste. Many of the skeletons showed no trauma, no arrowheads, no sword wounds, no signs of war. Yet entire populations vanished almost overnight. At first, these sites were seen as local tragedies, isolated events lost in time. But as radiocarbon dating and DNA sequencing advanced, a disturbing pattern emerged. These burials weren't isolated. They were connected by time, by geography, and by something else. Across all these graves, scientists began to detect genetic traces of the same ancient pathogen, a killer that swept through prehistoric communities with terrifying precision. A plague without name, without record. Until now. Was this the earliest global health crisis in human history? It all started with a child's molar. In 2011, researchers at a burial site in southern Germany unearthed the remains of a young girl, buried alongside her family in a shallow grave. Her bones told little, but her tooth, sealed for millennia, held a genetic time capsule. When scientists extracted the pulp, they found it. The genome of Yersinia pestis, the bacterium responsible for the Black Death. But this version was ancient, far older than the medieval plague that devastated Europe in the 14th century. This strain was different, primitive, muted, and yet lethal. Further excavations across Eurasia revealed the same genetic fingerprints, locked in the teeth and bones of others who died during the same period. Suddenly, what seemed like a singular anomaly became the first thread in a vast web, a prehistoric outbreak, stretching thousands of kilometers and lasting centuries. The discovery sent shockwaves through the scientific world. Could this be the origin point of history's deadliest pathogen? Had the plague haunted humanity for far longer than we ever imagined? One ancient tooth had opened the door. Now, researchers were rushing to uncover what lay behind it. The race was on. Scientists from around the world launched a coordinated effort to uncover the truth behind this ancient killer. Leading the charge were paleogeneticists, experts in extracting and analyzing ancient DNA from human remains. Using next-generation sequencing, they began decoding genomes from dozens of prehistoric individuals, spanning from the Baltic Sea to Central Asia. But the challenge was immense. Time had ravaged the genetic material. Most samples yielded only fragments, broken, degraded, contaminated. It took years of meticulous work, layer by layer, tooth by tooth, to reconstruct what little remained. Researchers had to isolate the pathogen's DNA from human and environmental sequences, like assembling a shattered mirror from grains of sand. Meanwhile, archaeologists mapped the spread of these burials. Patterns began to emerge. The victims weren't random. They followed the trails of ancient migration and trade. The earliest strains appeared in the Eurasian steppe, then slowly moved west, toward Europe. As populations shifted, so did the pathogen. It evolved, adapted, and became more deadly. But one question remained unanswered. How did a disease become this efficient, in a world that had no cities, no highways, no mass movement? Something didn't add up. The clues were in the DNA, but the key had yet to be found. Then, the breakthrough came. In 2018, a team analyzing ancient genomes from individuals in present-day Russia discovered the oldest known strain of Yersinia pestis, dating back over 5,000 years. But this wasn't just a genetic relic. It was a crucial piece of the evolutionary puzzle. Compared to its medieval descendants, this early strain lacked one critical component: the YMT gene, a mutation that would later allow the bacterium to survive in the gut of fleas, turning them into deadly carriers. Without this gene, the plague couldn't yet cause pneumonic or bubonic infections as we know them today. But it was already deadly, spreading through direct contact, possibly through saliva, blood, or handling of infected corpses. Its virulence was shocking for such an early stage. And as scientists traced its evolution over centuries, they saw the pathogen mutating, adding new genetic weapons to its arsenal. The tipping point came when Yersinia pestis acquired the YMT gene. Suddenly, fleas became mobile syringes. The plague could now spread faster, farther, and deadlier than ever before. And this mutation likely occurred before the Bronze Age, setting the stage for mass deaths and social collapse. The ancient DNA didn't just confirm the pathogen's presence, it revealed the moment it became a mass killer. Imagine it, a small Neolithic village at dawn. Smoke rising from clay hearths. Children playing in the fields. Then, fever, coughing, sudden collapse. Within days, entire households are dead. Survivors flee, unknowingly carrying the invisible killer with them. The pathogen moves silently, spreading from village to village, following the pulse of human migration across the ancient world. This wasn't a single outbreak. It was a slow, rolling pandemic. Over centuries, as people from the Eurasian steppe began migrating westward into Europe, they brought with them not only new technologies, like metallurgy and horse domestication, but also death. The early strain of Yersinia pestis traveled in their bones, in their blood, across rivers, forests, and mountains. Populations that had never encountered the pathogen had no immunity. The result? Collapse. Entire Neolithic cultures disappeared from the map. Settlements were abandoned. Burial pits overflowed. Social structures crumbled. It was not just biology. It was a cultural extinction. The ancient pandemic reshaped human demographics. It may have paved the way for the Indo-European expansion, wiping out rival populations and leaving fertile ground for new societies to rise. The Black Death may have been history's loudest pandemic, but this one, silent and unseen, was its prototype. It was the blueprint for biological apocalypse. We often think of pandemics as modern phenomena, born of crowded cities, international flights, and global trade. But the truth is far older and far more unsettling. The first Great Plague didn't need skyscrapers or airports. It thrived in silence, among farmers and foragers, traveling on foot and by fear. Ancient DNA has revealed what no historian ever could: that even in humanity's earliest chapters, nature had already written its own rules of survival and extinction. This prehistoric pandemic didn't just kill, it reshaped the world. It altered the course of human evolution, redrew the genetic map of Eurasia, and left behind silent markers in our bones, our blood, and now, in our science. Today, as we face new diseases and unknown threats, these ancient revelations remind us every microbe has a story, and some of them began before history itself. If you found this story as chilling and fascinating as we did, don't forget to like, subscribe, and dive deeper into the forgotten chapters of our past. There's so much more buried beneath the surface, just waiting to be uncovered. Because sometimes, to understand the future, we must first unearth the dead.